for my movies. I'm so glad. Before I get started with my presentation of Newton's second law of gravity, let's look at a picture of Jeff Goldblum looking handsome. That sure is a handsome man. I love Jurassic Park. Anyway, let's watch that movie I made. It's good. So, I dropped a 213 gram can out of my hand in my kitchen. And from my foot to my shoulder is about 150 centimeters. Yep, I look handsome without a head. Let's play that. Do. Oh man, that really sped up at the end, kind of like what gravity does. Alright, well, let's look at the stuff we're dealing with right now. We're trying to figure out or anticipate something's position, aka the final resting position, based off its initial position, plus the net of all the forces acting on it. In this particular experiment, we're mostly doing just with weight force. Then we're going to do weight force with drag. So anyway, that's divided by the mass of the object times delta t. And our weight force, we decided was going to be the ball's mass times g, which is a constant, times j hat, which is just the direction that's falling, which is downwards, dummy. Little g, that's 9.8. We figured that out because we were told that. Anyway, let's watch a brief program on what's going on. This particular program we're going to run first without drag, with just the weight force, aka 9.8 times my grammage. Is that a word? You tell me. Okay, it's starting now. And there's the ball. It's going slow, and then it goes bam, drops so fast. And here's a graph. We all love graphs. That shows us what we pretty much expect to see. I don't see anything like really out of the ordinary with this battle, Larry. Uh-oh, wrong thing. Let me move this here. Alright, close that. Close that. Maybe not. Close that. My program's still running. Alright, whatever. Anyway, now let's try making the net force not just the F net, not just the weight force, but also the drag. Let's see if that makes any significant changes between that's 150 centimeters. I really don't think it will. Oh, geez. Turns out it looks very similar. It looks so similar. I'm disappointed. Anyway, so I don't figure that I would really drop it high enough for it to reach any kind of terminal velocity, nor did drag really have a huge effect on it. I think if I maybe dropped it off of a building, then it could reach terminal velocity after a while. It would especially reach terminal velocity a lot faster if I were to throw it down off a building. Oh, that's still running. Let's just go ahead and cancel that anyway. Alright, let's look at a graph of what we're talking about. Oh, there's Jeff. He's looking good. Alright, so check this out. Here's what I observed happening. Here's what the model predicted would happen. Notice that you can't even see a red line. That's because it's behind the yellow line. It's camouflaged. I believe that's because there wasn't a huge difference between such a short amount of time and short distance between with drag and without drag. The reason why this is so far off is, I assume, like you can tell the slope isn't terribly different, except for at the end where it hit my blanket and I was still recording. Because right here when I was recording, it was in my hand and not moving, but it was counting its position. So it didn't really start dropping at 0. So that's my bad. That's why that would be off. But it shows kind of what was going on if you could just move this guy over here. And I can show that the red square or line is actually behind the yellow line by check out this data, brother. Let's look at some random point for one line. There's that. 0.00117. Negative that. Excuse me. Let's check 175956, blah, 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 blah. Over here, 0.001176. It's actually in a different position, but not really in a different enough position to be able to show it on a not very small or large graph. In any case, the model does reflect what was happening in reality, other than my poor filming and holding on to the thing too long. Yeah, let's look at Jeff again. Okay.